How you doing? We're in chapter 8, and chapter eight's really talking about the removal of residual particulate matter. When we talk about water reuse, we want water in generally that is free from turbidity. Now, a couple reasons for that, um, because to properly disinfect, typically we would like to remove any kind of turbidity in there on page 375. And just from a visual standpoint, obviously the more turbid the water, um, people view that as contaminated. And so um, in general, this is question one. In general, secondary effluent contains colloidal and suspended particles along with aggregate clumps. um, so particles have a range of the impact of quality water depending on their physical, chemical, and biological properties. So you can see on page 376 the contaminants, and then kind of where you know the technology on the bottom in terms of particle size that we need to remove. Obviously, reverse osmosis is probably on the top end there to remove any kind of solids, and then on the other side, of bigger pore size, you have your sedimentation depth and surface filtration. For years we've used sedimentation and surface filtration, and so we're going to go into those. But we're trying to remove pathogenic bacteria, protozoas, viruses, algae. All those things that we are trying to um, remove. Right? There anything that causes turbidity. So turbidity on 384, turbidity is a measure of the light transmitting properties of water. It is another test to indicate the clarity of treated water with respect to colloidal and residual particulate matter. So really, we want to see turbidity measurements require a light source and a sensor to measure the scattered light. So if you have a lot of turbidity in your water, your light is obviously going to scatter or not make it through. To make it in layman's terms, if I had a cup of water and I shine a flashlight through it, the more turbid the water is, the less the light's going to go through, right? And it's going to be reflected. And that really comes into play when we talk about ultraviolet radiation, because if you have really turbid water, you cannot properly um, remove it. So your technologies for removal, your depth filtration, which is basically um, like layers of sand in a swimming pool. For those who haven't seen depth filtration, it's your typical drinking water gravity filter, right? So the water comes into the top, goes through layers of either anthracite coal, sand, or a combination. As the water slowly by gravity feeds through, the particles are going to get stuck onto that media surface. And then eventually throughout the day, we're going to have to reverse the flow, uplift the particles to remove them. So that's depth filtration. Surface filtration is more like your Siemens uh, Disc 40. And so it would be more like it's like a sieve action. So depth has depth to it. Surface would just be what my hand can catch before the water goes through. So it's very, once again, there are special technologies. Think of it like a seine that you would seine a creek with. Very similar to that. That's surface filtration. And then membrane filtration is you know tightly woven wound membranes that take pressure, external pressure, to drive the water. So think about it as my skin layer. If you would put enough force onto this layer of skin, if you had a pump that was forcing water through, my skin layer would reject impurities, and the clear water would move through my skin. Now, it wouldn't do much for my skin, but that gives you a indication of what reverse osmosis or membrane filtration, and then dissolved air filtration. This is where they use air and the solids, and it says it's a gravity separation process in which gas bubbles attach to the solid particles to cause the density of the bubble solids to be lighter in the water, therefore being able to remove. You can read about some of these, but once again, before we go into disinfection, typically we want to get the turbidity out of the water. And so especially for water reuse. It says, and I think this is question 3, depth filtration is one of the oldest operations for potable water. I mean, we've been using this for years. When I worked in a water plant, we did depth filtration. You can look at the different types of gravity filters. You have your conventional downflow, your deep downflow, and a couple other pulse beds and synthetic medium. But the idea of a depth filtration is we want to remove the solids and the turbidity out of the water, and in the water treatment, typically what we're trying to remove on a well is we're trying to remove iron. So you can do that by gravity or on 396H, a pressure filter. And so as it works is the water is pumped into an enclosed vessel. The influent pushes down, and the particulate matter and iron, manganese is taken out in the sand. And then you have the gravel, which keeps the sand from percolating through. And then eventually you have to backwash. So a lot of times with depth filtration, other than a few of these, you have some sort of back back washing uh, to remove the solids. Reading through this chapter, one thing when you're selecting a filter media is you have to know what you're trying to take out, because if you pick a medium that is too tight, too packed, too tight, you're going to use a lot of energy to push that water through that tightly packed medium. But if it's too loose, obviously you're going to get turbidity that will break through. And so, really knowing what you're trying to treat and your outcome that you're trying to achieve is important. Once again, on 415 is pilot studies. We want to make sure we do pilot studies. Surface filtration. This is question 4 on page 417. Um, we use surface filtration in our wastewater treatment, and basically you can see a disc filter there on page 419. The water is going through about halfway, and the filter is going in a circular motion. The water is going through, and it's stopping any solids. It's like a cloth filter, or some of them are stainless steel, and so it's trapping any kind of particulate matter that's trying to make it through as that spins. And then periodically there are power washing nozzles that are along the side of that, and will actually power wash that cloth media um, um, off, and then goes back to the head of the plant. If you can think about it this way, if you had a t-shirt and you cut it in a circle, and as it went through the water's trying to move through that circle t-shirt about halfway through that circle, and then as it comes up out of the water, that's where you're going to get those power washing action, and it's going to remove any kind of turbidity or particulate matter that lays on it. You can kind of see a view of that on 420. So you can have a cloth filter media, or like I said, I know that Siemens came out with a stainless steel plate. Membrane classifications. Once again, you can have a membrane, reverse osmosis, nanofiltration. When we talk about that on page 431, you have microfiltration, ultrafiltration, and then nano and RO. So your nano and RO is your greatest, tightest pore pattern, and then nanofiltration, and then I can't remember if it's micro or ultra after that. Um, there's the advantages and disadvantages. Membrane filtration is nice. It takes up, I believe, a smaller footprint. However, you have to do a lot of maintenance, um, and there's some chemical costs that go with it. Question 7 on page 445 is dissolved air flotation. Um, and it's basically what you want to use it for. DAF, air is dissolved under pressure in water to be treated according to Henry's law of dissolution. After pressurization, the pressure is released to standard conditions, creating millions of microbubbles. The microbubbles surround slow settling particles and float them for the surface for reuse. I've never run into a DAF. Maybe you work at one um, at your plant. Question 8 on page 454. Um, some of the issues that must be considered is the final use of the effluent. What are you going to use it for? The pilot studies, the type of disinfection you're using, right? Like if you're using UV, you obviously want your turbidity out. What site constraints do you have? What kind of economics do you have, right? Obviously, in a perfect world, would run everything through reverse osmosis, but maybe that's not uh, economic to do at your small satellite plant. So just all the things to think about. Thank you for joining with me, and I'm sorry for keep drinking, but it kind of keeps my throat from getting dry. But that's chapter 8. Thank you.